Einstein saying, God does not play dice with the universe. And then Niels Bohr says to him, Einstein, stop telling God what to do. In quantum mechanics, it's called the collapse of the wave function.
Post-quantum cryptography is being talked about a lot. Looks like 2027, 2028 is the deadline for many of these things.
We have proven that it is not a force. Gravity is the only phenomenon in the world that cannot be explained by quantum. I would say a large part of the last decade or so in at least AI has now been about fully embracing the power of matrices and tensors. So we control that experience. And therefore we can define that, when the voltage is applied, let me call it a 1 or let me call it a 0.
So in that sense, I think to completely, I would say decommission Intel would also be wrong, because there's many things that we know to be deterministic.
Maybe I was using AI in a more narrower sense, which is AI instantiated through classical computers, right?
Good morning, Abhishek.
Good morning, Dheeraj.
Welcome to Effortless.
Thank you for having me.
We have known each other for many years now, and I can tell you that I'm such a student when I'm in front of you. You're one of the people that I learn so much from, and that to me is just so exhilarating. In fact, we're gonna do some episodes on quantum when we learn computing together as well, just like I do with my fellow podcaster Amit Prakash. So thank you so much for coming down.
Thank you so much for having me. It's my pleasure. And to be honest, whenever I talk about these things with you, I just come away from it inspired. So I learn a lot more from you than the other way. So thank you.
Well, it goes both ways. For the sake of people who are listening to this, let's talk about how we met. I know that it was courtesy our CTO Ahmed Bashir. This was several years ago. But what has your journey been in the last, let's say, 20 years? Maybe go back to where you grew up and.
So I grew up across the country in India. Did my undergrad in IIT Kanpur. I was a gold medalist in physics Olympiad at the national level. So this is like a nice full circle moment for me. And, did my PhD at UT Austin, spent some time at Princeton as well.
That's very similar to where the two of us actually overlapped too. Like undergrad school, exactly the same campus.
Yeah.
And then...
Same major,
computer science. And then you come to UT Austin. The only difference is that I leave my PhD and you finish your PhD.
Yeah.
Yeah. And then you go on to do a postdoc at Princeton?
No, Princeton, I went mostly to the IIS because I had solved this 30-year-old unsolved math problem. And so Avi Victorson, who won the Turing last year, he had invited me to the IIS to give a talk there. We're going to learn a lot about some of the results of Einstein and others who basically was the first faculty member there. So after PhD, I left for industry and did a bunch of frontier security work at Apple, leading a lot of these technologies, initiatives in the company. And then left, co-founded this startup because I wanted to strike out on my own, following along your journey. It was also along like secure collaboration and how do you secure PI data and still enable sharing of this data between different enterprises. And Snowflake recently acquired that company, so I'm right now at Snowflake.
So this idea of secure sharing and collaboration, and you call it Samuha?
Yeah.
Samuha. What does Samuha mean?
Samuha is a Sanskrit for coming
Collection.
Together, a collective, and we felt that it's about enterprises coming together and then running these joint workloads. But we know that enterprises normally don't want to trust each other and they don't want to share PI, right? So how can you do that in a more responsible way? And this was right off the backs of Apple deprecating IDFA, Google announcing that they're going to take out third-party cookies. So in the absence of those pseudonymous IDs, there is no way to then join these data sets unless it's just PII. So there was a need to have like this trusted third-party entity, which could be the escrow-like environment for companies to go do this workload, joint workload analysis.
Fascinating.
So but yeah, I've always been in this security, AI at the intersection. That's like my sweet spot, I would say.
So the passion that you bring is around both security and AI. You've been there at Snowflake for 2 years now, or almost 2 years?
Yeah, a little more than 2 years.
So today, I'm going to learn with you, this whole journey from, not just Intel classical computer to the NVIDIA sort of, the whole AI revolution that's going on. It's also quasi-classical in many ways. Maybe we'll inch towards TPUs, and finally we'll talk about the need for quantum computers. But along this journey, we have to first understand quantum mechanics. And that's the episode that we're doing today. It's like the death of if-then, in some sense. And you and I were talking about the analogies from 100 years ago, the end of the if-then world. So maybe talk to everybody about the end of the if-then thinking.
Yeah, so similar to the GPT moment that we have right now, in 1925, we had a similar phenomenon where the if-then for all the classical physicists was shattered. And why? Because Heisenberg and Schrödinger came up with this theory called quantum mechanics. And it's basically saying that at the fundamental level, everything is just stochastic, right? It is not deterministic at all. It just so turns out that with high probability, the outcomes can be predicted, but inherently in nature, everything is probabilistic. And then there is this famous debate between Einstein and Bohr. And just to give you a sense of how difficult it was for people of that era to accept non-determinism, like Einstein could not come to terms for decades after it. And Einstein arguably is a bit smarter than most folks in our community.
In fact, maybe before you get to that real debate, talk about the conference where he's sitting in the center.
Yeah. So, and this is also something we can flash for folks who are viewing this on a desktop or somewhere. But there is this conference called the Solvay Conference that was in 1927. There is a picture that some of you might already know, which has Einstein and Marie Curie and basically the who's who. And 1927 was the culmination of quantum mechanics having entered the main stage. You will see in that picture Einstein is at the front row because at that time he was the most dominant figure, because general theory, relativity, special theory, they had already been laid out by him. You will see Bohr on the second row somewhere in the corner. You will see Heisenberg, Schrödinger, just young folks somewhere in the second row. In that picture, Marie Curie is the only person who has won 2 Nobel in 2 separate fields. As far as I know, she's the only person who has won Nobels in 2 different fields. But it basically shows that the front row, at least Einstein of the world, they were the pro-determinism world. Like today, right? In a software, we say we rely on deterministic software, and we are coming to terms with this LLM world, and it is a process. But I would say the 1927 debates had already started. Even in 1935, you will see Einstein writing out papers while at IIS saying, is quantum mechanics really accurate? And there's a famous EPR paper as well. So he was not okay with this non-determinism nature.
So I think you mentioned this thing about God and the game of dice. Say more on that rhetoric that is going on between him and Niels Bohr.
Yeah, so Bohr was largely aligned with this quantum behavior. He also had this Copenhagen Institute. Einstein still believed in deterministic phenomena. And it so happens that the way quantum particles work, it's always in a superposition of a bunch of states all at once. It's very hard to interpret it. And he just felt that something was unnatural. And he even had this side theory that maybe there are latent variables, just like we try to do latent variables in AI today, right? Whether it's sparse autoencoded and so on. He thought there are some latent variables, but then that was also disproved later. So there is this famous debate ongoing, and the most colloquial and the catchy one is Einstein saying God does not play dice with the universe. And then Niels Bohr says to him, Einstein, stop telling God what to do.
This is profound, so I'm going to repeat what you just said. God does not play dice with the universe. And then Bohr retorting back, stop telling God what to do. And this is because they're grappling with this idea of non-determinism. Was Bohr also grappling with this? Was he trying to look at he famously looked at the Hindu Upanishads to understand non-determinism a little bit more. We even saw some of that come together in Oppenheimer, looking at Bhagavad Gita and the paradox principles and things like that. What was the paradox that they were trying to capture from Upanishads, if at all, to say, look, this is probably the way the universe works?
I think the way to capture that would be they were trying to understand reality, and the way quantum mechanics works is every fundamental particle, they are in a superposition of a bunch of states, and it's not at all straightforward to comprehend how a particle can be in so many states at once. And what we also know in quantum is the moment you measure something, then you will only see one of the possible states, right? If it's an electron spin state, it could be in any superposition of 0 and 1. We don't know what state it is in, but the moment you measure it, it'll either be 0 or it'll be 1. I think what they were trying to grapple with is this notion of, is reality once you do the measurement? Is that what we call reality, or reality is anyways non-determinism? So that's what they were trying to understand. In quantum mechanics, it's called the collapse of the wave function. And the wave function is basically encoding this superposition that a particle can be in. And the moment you measure something, that's when the wave function collapses. You get like a deterministic position where it will be, right? And it goes into this, what is reality? Is it what we see? Is that reality? And there was this philosophical thing, I think one of the scientists went, is the moon there or not? And only when I look at it, is that when it materializes? And that goes a bit into the philosophy. But you will see that quantum mechanics is very hard to interpret, which is why a lot of these eminent scientists, Schrodinger, Heisenberg, they would resort to texts like this to make any sense out of it. What they were extremely good at is predicting the outcome. Even Feynman, they have all resigned to the fact that let's not try to understand why it's taking all these crazy paths. The theory works because I can predict to like 10 decimal points what the magnetic moment of a quantum particle will be. And that's how they came to terms with it. Like they can predict outcomes, and it is still an open problem as of December last year, because Jim Khalili had this was mentioning in the Royal Institution. We still need a good explanation of why it does it this way. How do I interpret it? The Schrodinger's cat thing is the right. The cat could be dead or alive based on that release of the poison. So I would say that's why there's a multitude of things. What is reality? Is it only the post-measurement thing, or not? So for those reasons, these scientists would go to these texts.
Well, we are gonna at some point in this episode, and even in the future episodes, talk about probabilities and probabilistic computing, and the move away from scalar computation, which is what Intel was known for, x86 was known for, to vector, to tensors. But maybe before we get there, let's talk about quantum particles. Like, what's the structure of these particles. And I know it gets a little bit into physics, but I think it's good education for even people in computing right now to understand a little bit of the nature of physics as well.
Yeah. So maybe we can use this simple atom example that we had pulled up in the past. So in school, what did we learn? We had an atom. It had electrons outside, and then at the center you'll have the like protons, neutrons, right? And for the longest time, we thought that was the model and that was the fundamental state from Rutherford. Then, as of 1970, we kind of closed out the entire standard model of particle physics, and we now know that the fundamental particle, electron, is one of the fundamental particles, so we got that right. Protons and neutrons are not. They're broken down into quarks. So each of proton and neutron are made of 3 quarks.
And only 3 quarks.
Only 3 quarks, and even a particular combination. The proton is 2 up quarks and 1 down quark, and the neutron is 2 down quarks, 1 up quark. There is no meaning to up and down. Physicists just ran out of creativity. It is just called up and down. One of the quarks is also called charm quark. So there is no meaning into this.
By the way, just as an aside, when you're doing the physics Olympiad, were these things as charming as they are right now? Was all this revealed even 15 years ago?
No, I would say the Olympiad era was still like you're so young and you're being fed special theory of relativity and general theory of relativity. So it felt more equations, and it's only when you get this kind of perspective that you're able to go back in time, right, and truly appreciate. And if your listeners are interested, there are like a good set of introductory books we can go into. But I would say I did not appreciate physics and its role in AI and other places without this added perspective, right, over the last 20 years.
Fascinating. So going back to you talking about matter particles.
Yeah, so matter particles, the good news is there are only 3 matter particles we are made of. All of us are made of electrons and the 2 quarks. There is one other thing called a neutrino. We're not going to go into it. It's just a trillion of neutrinos are passing through us at this very second. They come from space and they go. So we'll not confuse anyone. There are also some other heavier, unstable matter particles which also come and go. We are not concerned with it, but we are just made up of electrons and these 2 quarks. And these two quark types are basically the protons and neutrons, and that's it. That is the periodic table for matter particles. And similarly, all the force that we used to learn as a kid, which is electromagnetic force, strong nuclear force, weak nuclear force, and gravity.
Strong nuclear force and weak nuclear force and gravity.
Yeah.
And all these 4 forces are non-overlapping.
They're non-overlapping, and gravity, we have proven that it is not a force. Gravity is the only phenomenon in the world that cannot be explained by quantum field theory or quantum mechanics. For gravity, you have to resort to Einstein's general theory of relativity, which is a whole...
and they're trying to bring the 2 together somehow, right?
Yeah, so quantum gravity is the attempt to unify the 2 to make one single theory. And one school of thought is trying to gravitize quantum mechanics, and the other school of thought is trying to quantize general theory of relativity. But we don't have anything yet.
And what are these force particles called?
So the most common one, the electromagnetic force, is mediated by a photon, which we have all known about. So if you recall, right, we used to learn light is a particle. Basically, all of these fields have particles associated with it. The electromagnetic field is represented by the photon particle. Similarly, the strong nuclear forces, we have the gluon, and then we have some other particles as well. But I don't want to throw too many new terms, but the matter particles are called fermions, the force particles are called bosons. But it is interesting to note that everything is treated as a particle, right? You have electrons and quarks, which we are made of, and then we have all the forces, which are also mediated through particles. And
electrons and quarks is what makes up all matter. And then the force particles are basically interacting with the matter particles.
Yes, so all these particles interact with each other. So electron and photons will interact with each other. That's what it means to have an electron move in the presence of a magnetic field. It's just two particles interacting with each other in funky ways, which are studied through what we call Feynman diagrams. Very simple diagrams that Feynman pioneered, similar to these free body diagrams we used to do in our 11th and 12th.
Mm-hmm.
So I do want to clarify one thing about what physicists mean by a particle. And just I'll take a minute. Particle, like electron, these are not solid objects with dimension. They are dimensionless. And what they mean by any of these particles, right? The electrons and quarks on the matter side, and the photons and other things on the force side, and the bosons more broadly, and Higgs is another one of those bosons. We can leave that for now. Is there's only an electron field. There's one electron field across the whole universe, and a field is, think of it like a fabric where every point in space has some value associated with it. And an electron or a particle is supposed to manifest when there is an excitation, a localized excitation, and think of it like an energy packet. That localized energy packet is what they call a particle. So it's not like a solid thing. It just so happens that it has particle-like behavior. So colloquially, it's fine to say particle, but the real fabric of the universe is just you have a large electron field, and we all share the electron field. Like excitations in your side become your electron, but nothing separates us other than that, right? It's still the same field we're all part of. Similarly, there's the electromagnetic field. There's only one field, and at every point there is a vector associated with it, right? And
so you mentioned electron field and then an electromagnetic field. Are they two different fields?
Yeah, every one of these particles, they have a field. They just have one field across the whole universe. Mm-hmm. And these particles are just energy instantiations in that one single field. So in the electron field, whenever there is some excitation, we call it he's an electron, right? Similarly, in the electromagnetic field, if you have a little excitation, we call it a photon. And that's what it means when two particles interact. It's just that the two fields are interacting, the energy packets are interacting with each other. Mm-hmm. So that's what the particle is in reality.
I mean, in our world, at our scale, like obviously there's a population of 8 billion people. And in some sense, I have a field right now, you have a field as well, and we are interacting.
Yes.
So is that the way to simplify and say, look, we at a macro scale, this is what is happening, and at a micro scale, it's also the same?
Yes, I think that's a good way of saying it. We have to say that, we should say that there is one electron field. There's only one electron field, and some of the excitations in my localized electron field give rise to my particles, and similarly some of the localized interaction in that same electron field but happening in your location is giving rise to you, and that's also what gives you mass, right? It's mass is just the energy, E equals mc squared.
So 1940s, 50s, 60s, especially 50s and 60s, we were trying to just put all of this into computing, through transistors.
Yeah.
Say more on what were we trying to really do to really come up to the world of zeros and ones, which we'll now say that it was unnatural and we should unleash back the nature again. But what was going on in the 60s or 50s and 60s with transistors?
So I would say 60s and all were a celebration of this theory and finding applications. And it so happened that...
So which theory?
Like the quantum mechanics, Schrodinger's equation, being able to predict electrons' motion and movement. The most natural thing to do was to, what I call this, analyze it in the smooth out effect. Like stop worrying about individual electrons, but observe it from a current standpoint, because that is much more predictable. That's more classical, if you will. So what transistors effectively did was, with the way you have doped the P and P of that, If you apply a small amount of voltage, then it gives rise to a current and a larger voltage. And if you stop that, then the electrons stop moving, right? And then that small amount of voltage helps it climb up the hill. And that presence or absence of threshold voltage is what zeros and ones effectively were. So it felt a bit roundabout, where you're harnessing the power of a quantum particle, and quantum by definition means discretized, right? You're turning it into a smoother effect through current and voltage, and then you're using that to again go back to encode zeros and ones. And to your point, I think what quantum computing is trying to do is to go back to the roots and see if you can directly harness the qubits, which are represented by the different states of an electron, or the different states these particles take.
It's very interesting, and it's still so profound and difficult to fathom. The fact that we are in this quantum world in nature, we were trying to put it back into zeros and ones. Then we realized that what x86 architectures were, building on scalars, working on scalar data, was going to be hard to build a more intelligent computer on. So it was a very deterministic way of doing computing. So we lost a lot of the non-determinism as we were trying to shove all these electrons into transistors, into zeros and ones, into scalar math with complex instruction set, which is what Intel is known for. And here comes this idea that, hey, we need to do probabilistic computing. And this idea of linear algebra and matrix math and matrix multiplication. And then we'll talk about tensor math and tensor multiplication. So what are we unleashing in the last 10 years? What have we unleashed that is taking us closer to nature than ever before? And so take us through scalar math to vector math to matrix math. And is this what nature is all about?
Yeah, I think your Intel scalar example is a good anchor point around this. I would say a large part of the last decade or so in at least AI has now been about fully embracing the power of matrices and tensors. And
explain to people what a tensor is compared to a matrix.
Yeah, so if a matrix effectively is a two-dimensional object, but there is nothing stopping you from adding another dimension or so to this set of, let's say, real numbers, right? And that is used very, very heavily in all of our AI architectures. But we can stick to just a simple matrix for now, which is you have a 2D set of numbers, right? And we'll see how powerful it is. You would be surprised to know that all of quantum mechanics, and you can check out Leonard Susskind's book on quantum mechanics, can be worked out, all of the math, including Schrodinger's equation, by just treating the state of these, let's say the spin state of an electron as a vector, and then any kind of operation on that quantum particle represented by a matrix, right? So what it's trying to say is that in the physical world, the way you impact a spin of an electron is by applying a magnetic field a certain way, and then it rotates, and now it's in a different state. All of the phenomena can just be represent the qubit as a vector, and then represent this thing here.
But you got to a qubit, which we'll talk about with QC, quantum computer. But just going from scalar to vector, you're saying is the natural state of the world.
Yeah.
Right?
Yeah. And this is true even on the force particles, by the way. The force particle we briefly touched on, they are, except the Higgs boson, which is a scalar, everything else is a vector. Like the electromagnetic field, I said, right, it's a fabric where every point in the universe has a value associated with it. You can think of it as a vector. And there's something called a graviton.
And by the way, 3 dimensions, n dimensions, like what is this field like?
The field is basically this. Like you can imagine it in a very physical way of space-time, right? So you don't have to go n dimension there. It's just this. Every point has some value associated with it. In the electromagnetic case, it's a vector. whereas for the Higgs boson, which is the mass field, the field that gives everyone mass, rest mass, that one is a scalar, right? So already most of our fundamental forces are either vectors, or in the case of graviton, it's a tensor, right? So whether you're talking about
you said something with, in the case of a graviton, it's a tensor. Explain graviton and explain why it is more complex than vectors.
So my take on this is, so graviton, the reason you don't see it listed in this periodic table of standard model is it is not yet proven that, remember we were saying they're trying to combine the two fields, quantum mechanics and Einstein's general theory of relativity, which is gravity. So they're predicting that gravity could also be mediated by a similar particle called a graviton, just like electromagnetic field is mediated through a photon. And in order to work out the math, it was not sufficient for the graviton to also be a vector, and they needed a tensor, higher dimension. I'm not surprised, because if you look at Einstein's general theory of relativity, all of it is based on this tensor, which captures the space-time fabric at every point in space-time, right? So I can see the parallels there, why you needed a tensor, because all of general.
And by the way, it's a 4-dimension vector then, basically.
Space-time is 4-dimension, x, y, z, and t. Mm-hmm. Today, we do not know if there are latent dimensions. That's what string theory and other theories come at, saying there might be latent dimensions, and we are observing just the 3D and time. Mm-hmm. 3D and time is still something we can appreciate. Mm-hmm. You have lost everyone.
When I was watching Interstellar, I got confused, man. It's like, there was so many dimensions to it. Yeah. And how you're moving from this world to that world, and from this dimension to the other. It does get a little sort of hard to actually imagine, because, in fact, nauseous a little bit,
It's very, very perplexing. And the thing about Interstellar is it's deeply centered around wormholes. That's how you can beat speed of light, because if space-time is so curved because of a heavy body that maybe you don't need to go like this, you just cut through a wormhole. And that's how they were able to move that fast. Right. Otherwise,
not that it happened. So for the audience, it's like
it's a movie.
It's a movie.
But if folks are really interested, just Google the EPR paper of Einstein, Podolsky, and Rosen, and
this is 1935. 35.
I think 1935 is EPR and ER. That's where the famous debate happened between the Roger Penrose and others. If you Google, you'll see that what they're trying to say is, are wormholes as equivalent to quantum entanglement or not? It's much esoteric stuff, but if you are interested in understanding what wormholes are and how they relate to quantum entanglement, definitely check it out.
Did they actually give him a Nobel Prize for that paper, or is it?
No. I think
it was
for
mostly
photoelectric.
Was
still quantum?
So it's still quantum, huh?
I don't think he liked that.
Really? You think that they were trying to fold him into the quantum world?
Yeah, because
by giving him the Nobel Prize.
He never got it for general theory or special theory of relativity, which arguably were very warped kind of things. Like, I'm just amazed how he came up with it. And it's also so deterministic. Unlike quantum, you can just work through the math. It's intuitive. And it'll make sense to you. General theory of relativity, you're just following a set of principles. But quantum mechanics is just, you cannot make any sense. You can predict the outcome. You can say this is the state of the electron, but that's about it. Similar to our LLMs today, right? Is these massive architectures. It gets it right. And we just keep struggling.
We just don't know how.
Yeah, we're trying to do the interpretability thing, or the latent dimensions. So I see a lot of parallels.
Yeah. I mean, if anything, businesses will struggle on. I mean, we talk about explainability with LLMs, and lawyers are going to ask for this. Juries are going to ask for this. If you made a decision to deny, let's say, insurance to someone, And it doesn't look like we can always explain how the LLM worked.
Yeah.
I mean, maybe, and I've been thinking hard about this, the quantum phenomenon, or even the classical phenomenon of principle of least action. Uh, Talk a little bit more about principle of least action and the world of probabilities that even light or any sort of matter particle or even force particles actually go through, and we'll connect it back to what we're trying to do with LLMs and optimizations and gradient descent and things like that. So let's start with principle of least action.
Okay, so principle of least action is basically a classical concept. It did not come from quantum world, and it's saying that particle will always take the path of which minimizes a certain objective function. It should be no surprise to the audience here. That's exactly how we do AI as well. We pick an objective function, we minimize it.
And for those of them who don't know the objective function, like in the world of LLMs, what is the objective function we're trying to minimize?
Let's say it's a loss function, right? How far we are from the ground truth, right? And you
which is the
it.
next token prediction.
Yeah, you can set it up for any kind of labeled set distribution, and you just measure some kind of you want to penalize the loss function when you're off from the current from the correct label, and if you hit the label right, you don't want to penalize it. Mm-hmm. So if that's your loss function, maybe you average it across your some sample set, and you're trying to figure out the right configuration of weights so that next time you pass an input into that function, you actually get what was the ground truth on the label side, right? And these can be encoded through a variety of mathematical function, and all gradient descent is a step-by-step way to go down the hill and find the least, let's say, local minima of that loss function, right? I say that very in particular because in a lot of the quantum phenomena or in the classical world, they did not need to do gradient descent to minimize their loss function. They understood it so well that they could just give you analytical solutions to where the let's say what configuration of weights in an LLM world will give you the least amount of loss, right? So in LLMs, it's just so hard that the step-by-step gradient descent is the only thing we can think about. But in the classical world, where they were trying to, and I'll soon tell you what their objective function was, the function they were trying to minimize, it was fairly intuitive to even calculate from first principles, saying, you know what, this body is going to go like this and like this, right? Simple examples where you're trying to say that you have a photon, it's traveling in vacuum, and then it hits atmosphere or water. We know it's going to bend because here it slows down. It's not speed of light anymore in vacuum. So we ourselves can do the math and say this is the path it will take, right?
And it is the principle of least action.
It'll use something called the principle of least action, and least action is so just like we worship our loss functions, physicists love something called a Lagrangian, which is just kinetic energy minus potential energy.
And it's just a loss function.
Yeah, it could go either way. They're not calling it loss, but maybe it isn't. You're trying to minimize it, so you're right. But it is the integral of the Lagrangian over that path, and they are trying to say that which is the path that gives me the minimum of for this value, right?
Which is basically principle of least action.
Yeah. In a way, yes, you're right. And with that, you can show that if you have vacuum and then you have a body of water, the photon is going to hit like this and this, right? Remember, we used to learn all these things around refraction and others. What's the angle? So they could do all these computations without needing to look at a loss function, do gradient descent to come up with the correct path. It so happens that for LLMs, because the set of weights is just so vast and the function of these weights is so complicated that one cannot just analytically tell you that, hey, if you set the weights to be this, that's going to be your minimum. We resort to gradient descent. And quantum mechanics, what their tribute back to classical world was that Feynman and everyone blew up people's mind by saying that, and maybe we can also put that picture up from his book. If you have a mirror here and a light source at one end and your eye on the other side, the light actually takes all possible paths, right? It is not just taking the symmetric path that we learned about. The symmetric path happens to be the least action path, but it also does take these other paths, and it so happens that all the neighboring paths, which we believe are unnatural, they're still happening, but they do destructive interference and cancel each other out, right? So in that sense, they're showing, quantum world is showing the classical world that we subsume you as a theory, because at the smooth out effect, all the crazy paths or the hallucinatory paths have been cancelled out.
Hallucinatory paths. You use the word hallucination with obviously a certain intent.
Yeah.
I think you're probably also trying to say that hallucination is not a bug, it's a feature of LLMs, of AI. It just so happens that we're trying to reduce them to get to the most natural, most probabilistic answer, which is the next token and such, right? I mean, what do you mean by hallucination in the quantum world, and why is it important to keep them as is?
That's a good point. So let's talk about why hallucination. I mean, quantum mechanics is not calling it hallucination, but it is clear to everyone in QM that everything in quantum is mind-boggling. So
and it's just about probability. At the end of the day, it's about lower probability.
Yeah, and they all have each of these. See, if you take the mirror example, the mirror is sitting horizontally on a table. You have a light source on the left side, and you have an eye sitting on the. You're looking at it from the right side. So normally we would expect the light to go in the center of the mirror and reflect back to your eye, right? And let's assume that there is a physical block between the light source and you, so there is no direct path to you. It has to go through the mirror. So it is. See, here's why hallucination is a feature for them. It is true that light is taking all possible paths. It's hitting obliquely the mirror and then also going back to your eye, which is totally unnatural. And they all cancel out. But the reason it's a feature is because the entire world has used that property to great effect. And it's called X-ray crystallography. And a lot of the AlphaFold work was using this data as well for the training data set. And how do they do that? What they're trying to take advantage of is, if light indeed takes all possible paths to reach your eye, what they did as an experiment is they blocked the center of the mirror with black tape. So let's put black tape in the center of the mirror. So you have ruled out what you thought was the only path. And now remember, I also said that any of the unnatural paths, the neighboring ones kind of cancel out in an interference pattern. So you also put these alternating black strips where you see the opposing.
And this is like the double slit experiment
it is very related to double slit experiment. Yes. If you look at Feynman's third volume, the first chapter is basically the gun experiment, the bullet experiment, the wave experiment, because these are things we understand, particle and wave, and then the quantum. So their point is, if you black out these strips in an alternating fashion, and if you black out the middle part of the mirror completely, you would say that there is no way I can see that light now, because where will it reflect from? But it does come to your eye, which proves that it is taking those paths. And that's how they study X-ray crystallography as well, because the way the lattice is made up of, you can think of them as some parts are blocked out, some parts are reflecting light, right? So there are all these ways. These are already used for many, many years, these hallucinatory paths. So I felt that we should also not immediately rule out something that looks unnatural. And a lot of the JEPA, some of these genetic prompter will evolve.
In fact, we should get to JEPA, but it looks like, I think the biggest thing that the entire software world, business world dealing with software is right now grappling with is probabilities. And that's the big sort of move out of Intel and deterministic computing to probabilistic computing as well. In fact, even search for that matter is like, probabilistic now. You're looking at k nearest neighbors rather than the world of databases, which was all about keys and values, and you needed to do a deterministic search for, and at best what we did was, give me a key which was, actually the greatest value less than equal to the k that I'm actually giving you. And that's as good as it got with indexes, for example, or lowest one, basically the either the lowest one which is greater than this or the greatest one smaller than this. That's kind of stuff that we actually ever did with indexes. But to go from there to k nearest neighbors is actually a really different way of thinking about even databases. What we're calling a vector database right now. Right. In fact, going back to this thing about fields, language, like every token that we're taking and mapping into embeddings in a vector database. What do you think about sentences and documents and tokens, these words that we are mapping to the world of vector databases and embeddings? How is that related to the idea of probabilities, k nearest neighbor, and just the notion of a field, language as a field, that we're trying to map everything into a field?
I think that's a fascinating thread to pull on. So just to double click on your question a bit more. So it is true that we have come a long way from this classical get me something less than t to let's actually do k nearest neighbors. And it speaks to some of this aspects of we may not see, it's not wise to prune everything at once, right? You need a slightly larger base and then you do the final pruning at the very end, right? All the search retrieval also do the same phenomena because coming back to this light taking all paths, you don't know if the suboptimal path that is looking suboptimal right now is just a function of some local minima. So you keep it around, right? So I do see some kind of analogy there with like how we had to go to k and n. And coming to your field analogy, let's see. So you're trying to say, can a vector...
Are we trying to put language in a field? Basically some sort of a tensor or a vector, 3 or 4 dimensions. Right now we're talking about 1,000 dimensions of a vector database. And we're saying every meaning is actually mapped to a field of 1024 dimensions or something, And is that the biggest thing we are unlocking right now is like, okay, go away from 2-dimensional database thinking, which is key and value, to
just map it in this larger dimension field.
This 1024, and then think about mapping everything to this n-dimensional vector.
I see. And then use some of use similar operators we use in the quantum world, which we anyways do, right? In AI, we use tensors, we use the matrix, but because it's higher dimension, we'll stick to tensor. So you kind of have the machinery from the quantum world as well. That's interesting.
Or at least just the way, why is this natural, moving away from Intel to NVIDIA, to tensors to quantum computing. At some point we'll talk about that too.
We should double click.
But why is this natural, and is this the way nature works? That's the thing that we are struggling with the most.
Yeah.
Is to say, is this something that just happened like serendipitously, or like, just because we had another architecture which is
transformer, it happens to do very well on the language aspect of it. And going back to some of the other quotes you were showing me, right? Like, is language limiting? Are we limiting ourselves? And maybe if we go multimodal, that's where the real value of this multi-dimension field will come in. And maybe language is enough to capture in a smaller dimension. But like some of the stuff that you're showing me around visual perception, having an order of magnitude more signal, that's where the real value of this high dimension field would truly come in. But it's something we should definitely
I mean, and obviously, to me, the most important realization is that we are living in the world of probabilities, and we were constantly trying to make it deterministic because it was easier to do the math. But now that we have started to think hard about linear algebra, matrix operations, tensor operations, it's just nature. This is not unnatural. In fact, the 60s, 70s, 80s, and the last 50 years of computing has been unnatural. We are really unlocking more nature in some sense.
Yeah.
Right?
And I would say that all of the LLMs, they are probabilistic, and the whole idea is how can we make sure that the next token or whatever the outcome is, we can predict the correct one with high probability. And we might have to come to terms that it will be a stochastic game at the end of the day, and we will try our best with ongoing technology or with maybe TPUs and etc. Other future tech to reduce or suppress the probability mass for these non-real paths, or the paths that we think are incorrect, right? So we could do some kind of probability adjustments by applying certain functions, similar to how wave functions also work, right? Just because a particle has a very smeared out presence doesn't mean it stays like that. You can, which means every place can have equal probability. You can apply a certain function or certain natural thing to it. Let's call it a magnetic field, which is equivalent to a matrix multiplication. Once you do that, then suddenly it becomes very localized. So even in nature, you're able to do physical operations on these quantum particles, and you turn a completely smeared out thing into a very pointed thing. So then you're able to then pinpoint it with higher accuracy.
And why did you say equal probabilities? Like, is it really equal everywhere?
It depends how you have set up the particle. For example, if I take a very real example of an electron, one of the quantum states it has is called a spin, and it can be in any superposition of the 0 spin and the 1 spin. What I mean by equal is you can set up the electron by applying the magnetic field in a certain way, so that remember when I said anytime you measure the state, it's either one of the two bases. You can set it up in a way where right now it is in a superposition of the 0 and 1 states. You don't know where it is, but the moment you measure, it will be with half probability it will show up as 0, and with half probability it will show up as 1. And you can do it by setting this experiment up 10,000 times each time you measure, and it will be roughly half-half, right? That's what I mean by the quantum particle is equally probable to be in either of those states. We just don't know which one. It's in both states right now. That's called a superposition. And the way at least quantum computing works...
So there was an intent to have half of it being 0 and half of it being 1.
Yeah.
And why is that any different than the way we applied voltage to it in the 60s with transistors? Like, what is the difference between this thinking and the thinking from 60s on applying a voltage and basically having be a 0 or a 1?
That's a very good question. The reason is in the transistor world, we want to control when it will be 0 and when it will be 1. So the way the P and P junction is set up, we know that when you apply the current at the base, small voltage, electrons will start flowing. And when we lift it off, it will stop flowing, right? So we control that experience. And therefore, we can define that, when the voltage is applied, let me call it a 1, or let me call it a 0. In the quantum world, we don't know what will show up. It's just that the electron is in that state.
And you don't know what will show up.
When you measure it, it could be either 0, it could either be 1.
But didn't you say that there was a magnetic field that we could apply to it that will make it look like a 1?
Yes, you could change the magnetic field to be, let's say like this, then it will always stay in the 0 state. Similarly, you could change the magnetic field the other way and it'll always be in the one state. But then you just recover classical computing. The whole point of quantum is to prove that sure, I can also do classical. But if I'm going to invest that much resources to protect that qubit, because remember, the hardest part of quantum computer is how do you keep that stable, especially with multiple qubits, because any interaction with the field that we talked about will destroy it. So the hardest part of quantum computing is setting that apparatus. So if you're going to do all that, might as well show much more powerful properties than to recover the zeros and ones with full predictability. And in fact, all of the breakthroughs, whether it's the breaking of RSA and all, come from this kind of superposed quantum.
Maybe we spend a whole episode on that, because obviously post-quantum cryptography is being talked about a lot. Looks like 2027, 2028 is the deadline for many of these things, and looks like browsers have already moved in that direction.
And I saw Apple last week announced their PQC, because the threat of QC is real and it does compromise.
And by QC you mean
quantum computing. It's
yeah.
real, and it does compromise all of the public key encryptions, right, which are based on elliptic curve. Or
so we should basically spend a whole episode on that, because I know there's depth in it. But going back to your point, I think the world is actually beginning to grapple with probabilities, because it's the most important and the most natural phenomena. What else do you have to say about this move from scalars to vectors, from scalar math to vector math, tensor math? Anything you want to introduce to the audience about the difference between NVIDIA way of thinking versus the Google TPU way of thinking, and the fact that they call it TPUs versus GPUs?
That's a very good question. In fact, I wanted to do a deep dive on that differentiation, because if you look at it, all of the GPUs were focused on nailing matrix multiplication, right? They optimized the
which
hell out
are
of it.
two-dimensional things.
Yeah, two-dimensional things, and very very naturally over the last decade or so, researchers realized that of course we have to add the third dimension, fourth dimension, because then you can run it in parallel, right? So I have to see more details about the TPU architecture and why they're clearly they're optimizing for tensor, because they know that is the prevalent object, because no longer are we working just with this simplified version of 2x2 thing multiplied by a vector. But from a technical standpoint, I need to do a more.
Maybe let's do that maybe in one of the
something
subsequent episodes too, because it's going to come up, and I think the question is GPU brute force and is TPU's low power and it's more natural, and why is it that people are saying that TPUs are better and lower power than NVIDIA? There's probably something there that I don't fully understand that
we should learn more, because they might be just more optimized for these tensors. So we should see what is giving it that boost that they are claiming is not possible in a regular TPU.
And is it wise to say that going from x86, which is scalar operations, to GPUs to TPUs to quantum, is that a natural continuum? Like that's the way life would have transpired anyway?
So this is goes back to, we were discussing a while back on the crawl walk run that you were alluding to. Is this really the crawl walk run that was always intended to happen, which is start with the scalar, then go into GPUs, TPUs, which are still like faster crawls, if you will, and then is QC and quantum AI, as Google is calling it now, is that the real run? And which could take 10 years, but is that the real steady state? I would think so, because that is going back to the roots of quantum particles. But I also wanted to mention two important caveats. One is quantum computers are not necessarily that much more powerful than classical computers in all things. They are very good at three things, three kinds of things. and that's what they are very good at database search. And Grover is the one who's very well known for it. Also an IIT alum. Grover's algorithm can do search with a significantly faster runtime. All of encryption algorithm can be broken by quantum, and then all of real quantum phenomena can be simulated by a QC much better than by a classical computer we built, right? Because what better way to simulate all these molecules and protein molecules than using the QC, the quantum computer, which is simulated based on these electron properties. This is the first point I wanted to bring up. Quantum is not like a panacea that is strictly powerful than classical.
I mean, what you're saying is that for classical problems, you use a classical computer, especially if it's deterministic stuff. Why would you?
Yeah.
I mean, even today, as we think about, as you call them, agents and skills and knowledge, I mean, there's a huge need for deterministic SQL, where you apply natural language, use probabilistic ways to convert to SQL, and then you just get into deterministic SQL as well. So text to SQL is a very important piece of getting answers to questions. So you went from a natural language to a SQL 4G language to a deterministic computer to find you do relational algebra on Intel as opposed to doing any kind of linear algebra on something else, and there's huge reasons to actually have deterministic compute for that alone. So already we're doing hybrid world, I mean, in the world of DevRev, we talk about search, and search itself is hybrid. There's value for syntactic search, which is like, hey, give me things that deterministically point to this keyword from all the documents that there are. And from there to get to semantic search is like already one probabilistic sort of move.
Yeah.
And then to go from search to answers, which is how do I get to structured data? And I give you natural language, you convert to SQL, and SQL goes there to, I mean, there's a hybrid compute here where we have horses for courses. And then when you get to workflows, you do want to use Intel for a lot of high code nodes in a workflow using Python or TypeScript or JavaScript. And there's a need for that. And it could be the fastest way to get there rather than use the probabilistic path of a GPU and LLMs. I mean, we do work for companies where they do customer experience sort of deflection of tickets. But to route it to the agent, sometimes you don't want to take 3 seconds to route it to an agent because latency matters.
Right.
So there'll be many, many trade-offs for which you want to use deterministic stuff. To say, I know exactly what this needs to be. Please do not use probabilistic code to go through this because it's going to take time.
Correct.
So in that sense, I think to completely, I would say decommission Intel would also be wrong. Because there's many things that we know to be deterministic, or we understand that this model that we're giving it is well understood, well known. So therefore, let's go through Intel.
Yes.
And make it come back in 50 milliseconds or less.
Yeah.
Than having to spend a random walk to get to 2 seconds worth of an answer.
Yeah. No, x86 is still the answer for all of this because we have spent so much time optimizing the hell out of some of these workloads that are meant for x86 and the 64-bit equivalent. I wanted to add that if you want to learn more about the real power of quantum computers and any myths associated with it, definitely check out Scott Aronson. He does a bunch of... He's
also a UT Austin professor.
Yeah, he's UT Austin. Very, very well known. And you will get the real truth about what is quantum computer really good at. Right? It is not like an all-powerful thing. If you think about these predicting protein behaviors, right, at such a high dimension, classical computer run out of steam, and that's one of the big promises of a QC or quantum computer. I hesitate because I feel that if you look at some of the protein AlphaFold work, they have been able
Which has happened on TPUs or GPUs, you think?
I think they would have used
TPUs.
Google, right? So I don't know. I have to check, but I would assume it will be TPU, but don't count me on that. But the DeepMind work that is happening, see, they are able to do what the quantum computer goal was, which is protein folding and understanding super high dimension. So there is almost this side thread that is going around circles and no one is speaking about yet.
But there is I met with a Nobel laureate yesterday in chemistry, and she was saying that, what AlphaFold has given us is a picture of the protein. It's like an image, but there's a video, which is a function of the protein that is still missing. Like, how does it function? And that's a video versus an image capture. So we are still in the very early days of this.
That's a very good point, because I was going to bring up this topic of, is AI going to beat quantum computer to the punch, or is quantum computer truly needed to then do the temporal aspect
and
of
what
it?
do you mean AI is going to beat quantum computer to the punch mean? Because I thought that you use quantum computer to do better AI.
I would...
Because you make it look like, gravity and quantum are actually at odds with each other. To me, these two things... AI is just a more intelligent machine, and you go from GPUs and TPUs eventually to quantum.
Oh, that's a good point. So maybe I was using AI in a more narrower sense, which is AI instantiated through classical computers, right? Whether it's GPU or TPUs. So in that sense, I was saying that is AlphaFold, who has now done the snapshot of the protein, can they continue using AI on the TPUs to also give the time series as well, because that was the job of, or the goal or dream for quantum computer, because quantum computer can do it at much larger scale.
And probably in a second that otherwise would probably take 1,000 years for this thing.
Because even the TPU is running on, this is still classical quantum, if you will, right? What I mean by classical quantum is, it is still like transistors, and you're using the current electric current to encode zeros and ones rather than the qubits, right? That's what I meant by AI running on classical. But to your point, AI is much broader than that. That same intelligence principles could be run on a qubit system as well, but one has to build one.
And which is what Google is. That's why they're calling it quantum AI. They're not two different things.
Yes. Yeah. Maybe that's why they're unifying it. They have unified quantum and AI then, while physicists are still trying to unify quantum and gravity.
Yeah, you're right. This is fascinating. I'm just, we're scratching the surface of this, Abhishek. It'll probably take me 10 years to even understand the ABC of this. It probably took Einstein 30 years to respect probabilistic thinking.
Yes.
But going back to what you said about him and Niels Bohr, did they give a Nobel Prize to Niels Bohr ever?
I don't know. I would have thought everyone in that Solvay Conference has won Nobel Prize.
Well, maybe we'll put that as a quiz for the audience, see if they can actually point where Niels Bohr is, where Heisenberg is. And,
let's see if you can spot it.
Right, where Schrödinger is standing or sitting.
You'll spot Einstein and Marie Curie, but...
and I wonder if there was also... I could see that the Germans and the Belgians were probably sitting in the back or standing in the back versus the British still had a huge sort of presence in the front row. Einstein had he moved to Princeton by this time?
He moved to IIS in I think 1933.
I see. So right after Hitler's rise, actually, because Hitler won the election in 32, 33.
Oh.
So he probably came right after that,
I see.
Right in the midst of that.
Because I know he was the first faculty member.
I think he probably came after Hitler won the election in 33.
I see.
32, 33 actually. It's fascinating. There's so much history to all of this. I'm sure we can just talk about this ad infinitum. We got to do an episode on TPUs and why they're better than GPUs, if that. And we should do another episode on post-quantum cryptography, and of course, I'll do a lot more reading to understand this. I'm still, I would say, in my elementary school with respect to this, but looking forward to really do many more of these episodes with you.
Yeah, same. Likewise, I enjoyed it. And if it's any comfort to the audience, this is a well-known fact stated by folks like Feynman and others, that if you think all of this is something you have internalized, then you haven't understood quantum mechanics. At a fundamental level, they themselves know that this is completely weird. So
At least all we know is we can compute our way to the outcome.
We can compute our way out, but we do not know what's happening.
No different than the way LLMs are working, and the fact that we don't know why they work, because people are trying to figure out explainability, but they just work.
Yeah.
Right. So we are computing our way to the next token and the next token, and it seems to make a lot of sense. No different than the way physicists have actually said that.
Yeah, and I think there's lots of learnings to take from there and applied here, and not just the technology aspects, but also the framing and coming to terms with how nature works.
Great. Again, just turning full circle on this, the world of if-then has been shattered. It was shattered 100 years ago in the world of physics, and we are shattering all the determinism right now in the world of computing as well. And this is just natural. So going from Intel and scalar math to NVIDIA and linear algebra and TPUs is just the natural way of the world. And how we'll go from here to quantum and how we use that to really look at simulating everything in life will probably be a journey of the next 20 years. So one last thing for the audience and maybe their children, like what could they read? I mean, I know there's some books in the back to get inspired about the world of probability, the world of matrices, the world of qubits. Is there anything they can actually read? And I know you talked about Feynman, but maybe is there a book that you recommend from that?
Yes. So I would recommend a set of 4 books depending on what you want to learn about. If you want to learn about...
So anybody in high school, what should they read? Even simpler things about linear algebra or matrices versus QED, and then maybe anybody in middle school.
Okay. So I would say that if you're very curious, then definitely read about, there's a book called Quantum Electrodynamics, and it just explains the relation of electrons with photons. And you might think that's a very narrow thing. You just threw in 2 particles. But that explains pretty much everything around you, right? It explains what it means to touch this surface. I'm not really touching it. It's just the electrons here are repelling the electrons of the couch, and that's why my hand gets thrown away, right? Just basic things like that. You definitely take a look at QED, Quantum Electrodynamics by Richard Feynman. He does not use any math, and he also has a fun way. As you know, he's a prolific, charismatic speaker. No math, and that would be a good experience of how unnatural this world is that we live in. If you are into if you understand linear algebra, and if you're very much driven to go deeper into the quantum mechanics with just linear algebra, no special math needed, it's just matrices and vectors, then Leonard Susskind has a very good series. He calls it the theoretical minimum. He's at Stanford. He, unlike Feynman, believed there should be some math so that people can get that aha factor.
Are we seeing that book here?
Yeah, that's the second book called Quantum Mechanics, the light blue color. And Leonard does an amazing job with just linear algebra, right? And matrices. That's it. With that, you can do Schrödinger equation. You can study quantum entanglement, everything. That would be something maybe a high school or a college person can, maybe earlier than college, you can get into quantum mechanics.
Well, if nothing, they can vibe with ChatGPT or with Gemini to really understand a lot of these topics too.
And all of Leonard's content is on YouTube. Each of his series, both the quantum mechanics and the relativity. The relativity series, the first video has like 1 million plus views.
Are you talking about the Veritasium channel?
No. This is Leonard Susskind. He's a theoretical physicist at Stanford. If you want more, for middle school, I'll share some very nice links on YouTube. But this would not be middle school material.
I'm pretty sure there's something on Veritasium as well.
Yeah. Yes. So for the YouTube ones, you want to look at Veritasium and you want to look at ScienceClick. ScienceClick is by another... I think he's a grad student at Cambridge or Oxford, theoretical physicist, does an amazing job of animation. It'll be very clear, pretty much all of the fundamental concepts. So Veritasium and ScienceClick would be great
Beautiful.
for that. And then finally, if you want to get into quantum information computing, nothing beats Nielsen and Chuang. That remains the holy grail. But that's
It's a
very terse.
crawl, walk, run innovation.
That's very terse. So
Awesome.
I would not.
Awesome. This is amazing. Thank you, Abhishek, for really doing this. I look forward to the next several episodes on this as well.
No, thank you for having me. It was amazing to brainstorm and learn. We were learning every day. It's amazing. Nature never ceases to amaze.
Yeah, nature never ceases to amaze. With that, thank you.
Thank you.